Hello, everyone. My name is Sivaraman. I'm from the Liberal Arts and Science Academy, and I would like to thank my co-author, Dr. Xiao from Optum United Health. Today, I'll be presenting on a novel machine learning-based murmur detection and classification using sound feature analysis. Okay, so both the World Health Organization and the Center of Disease Control list heart diseases as a leading cause of death, both in the United States and across the world. And this is a shocking statistic that really needs to be addressed. So there are a couple of pieces of data that we can try to analyze. So typically, heart data is taken in through two main methods. The first being electrocardiography or ECG. This is basically where you're looking at the polarization and depolarization of several nodes across the heart. And this can provide information as to the timing of pulses or even arrhythmias in the heart. The other main method for data collection in the heart is through phonocardiography or the PCG. Now, PCGs basically listen to heart sounds. What differentiates them from a normal stethoscope is their sensitivity. But these PCGs can provide us information as far as the blood flow in the heart, or more specifically, heart murmurs. So let's first understand how sounds are created in the hearts. So heart sounds are created basically when the valves of the heart open and close. So in the cardiac cycle, there are two main portions. There's what is known as systole, which is the pumping of blood out of the heart, and then there's diastole, which is the filling of the heart. These systole and diastole can be seen as two major sounds in a PCG recording. These sounds are known as these peak sounds are known as S1 and S2. Between the sounds S1 and S2, a PCG recording is typically silent. That's because blood flow in a normal heart is laminar, so you wouldn't hear anything between these main sounds S1 and S2. Now, this allows us to define what heart murmurs are more specifically. So, heart murmurs are basically when we notice that there is some sort of abnormality or turbulent blood flow between S1 and S2. So, these heart murmurs can take on several different forms and can be characterized in multiple different fashions based on their shape, duration, intensity, location among the heart valves, etc. And several of these characterizations can be directly observed through a PCG recording. So for example, we can look on the table on the right. This is basically, if we look at the first row, basically this is like an example of an early systolic murmur. Early systolic basically meaning the heart murmur is occurring closer to the S1 peak. Now, the interesting thing about these heart murmurs is that every single type of characterization maps to a unique set of diseases that a patient could possibly have. So in the case of early systolic murmur, this could map to an acute mitral regurgitation, which basically means that there is a backflow of blood in the mitral valve of the heart. So while there is the main issue currently is that basically doctors across the world typically lack the experience to take a PCG recording and create a characterization, appropriate characterization for patients. So there's a high need for PCG tools in the present day. Now there are several PCG tools that currently exist, but these PCG tools are unable to do two main things. First is to give a description of the location of a heart murmur, and second is to give a characterization of the timing of a heart murmur. So both of these need to be addressed. Now, this brings us to the research question: can we accurately detect and classify the nature of heart murmurs? So to approach this question, I talked to several cardiologists and I had basically I had basically looked into databases, clinically verified databases that could be used as far as hard data analysis. So the one that stood out most to both Dr. Joe Xiao and I was the CIRCOR Digiscope PCG database. Now, this database contains over 5,000 patients with clinically verified analysis of each heart sound recording. So basically, each patient in this database contains recordings in each of the heart valves. There are four heart valves. They have four heart sound recordings. And each of these heart sound recordings are sampled at 4 kilohertz. And this provides a computational basis for heart sound analysis. Now, it's not directly evident how we should take and use this database. There were 2 sound features that we extracted from this database. So for every heart sound signal in the database, we basically converted the heart sound signal into the frequency domain using the discrete Fourier transform. And in the frequency domain, we split that domain into 18 frequency bins or subbands. Within each of these subbands, we were looking at 2 main sound features, namely the filter bank energies. The filter bank energies basically being the strength of the heart sound. Sometimes we refer to as the subband spectral energy. And the subband spectral centroids, which is basically you can consider as the center of the mass within the frequency domain. So with these 2 features, we proposed a new methodology for the classification of heart murmurs based on their location. So we first, the main issue is when working with such large data, so all of these heart sound recordings, we are basically calculating their these 2 sound features across 25 millisecond time windows for every heart sound recording. And this happens for every heart sound recording in the database. So this produces a distribution of sound features across the entire database. However, this is a very large amount of data to process. So what we decided to do is basically observe just the first 4 statistical moments of these 2 sound features. So the first 4 statistical moments being the mean, which is the center of the distribution, the variance, which is the spread, and the skewness and kurtosis, which basically represents our tailedness. These 4 statistical moments were basically used in order to create machine learning models for murmur location prediction. Now, there were a couple of features that we wanted to first observe from these statistical moments. When analyzing on the this is basically 2 charts. On the left, we have several box plots of the filter bank energies in a no murmur case. On the right, we have several box plots for filter bank energies in a with murmur case. What we notice going from a no murmur to with murmur case is that the distribution of these moments actually shifts. This is noticed in the mean. And a similar trend is actually noticed in the variance going from the left, which is distribution of filter bank energies in a no murmur case for variance, going to a with murmur case on the right. We noticed a shift in distributions. Now, similar trends were also noticed in the skewness and kurtosis features, but to a lesser extent. So these features basically so this is an unusual shift that's basically happening when we're going from a no murmur case to a with murmur case. So this provides some insight as to what machine learning models should be used. Now, we chose to use a random forest classifier as we could. Random forest classifier is a tree-based algorithm, and we could basically encapsulate this shift going from a no murmur case to a with murmur case. So random forest classifier basically uses a bunch of tree structures in tandem, decision tree structures in tandem to create a prediction output. And we are basically using this random forest classifier model in order to predict heart murmur location. So the proposed methodology, which we are calling HM Detect, basically takes every heart sound recording and splits it into 25 millisecond time windows. Within each of these 25 millisecond time windows, we're extracting some amount of sound features, the filter bank energies, and the subband spectral centroids. Now, remember, our goal is to try to characterize heart murmurs right now based on their location. So we're actually doing a slightly like reverse process. We're first trying to calculate which location a heart sound recording actually came from, and then deciding whether that location actually contained a murmur or not. So we put this as two stages. In stage one, we have a random forest classifier that is able to basically classify what location of the heart a PCG recording came from. And in stage two, we have a set of four actually random forest classifiers, each representing a different location of the heart that are independently used to basically create a prediction for whether a specific location or valve in the heart had a murmur or not. So all of this random forest classifier models were implemented in Python with Keras libraries, and scikit-learn and matplotlib tools were basically used for data analysis and visualization. So here are the results from these random forest classifier models. We'll basically take a look first at the stage one, which is classifying the location of a heart murmur. On the left, so here we have actually two Pareto charts of the feature importances for the random forest classifier model. On the left, we have the mean, and on the right, we have the features for the variance. On the left, we actually notice we have a critical few features for the random forest classifier model. These critical few features are, in fact, the first few features of the first few subband spectral centroids and first few filter bank energies. On the right, we actually noticed that the variance features did not have such a noticeable critical few. This critical few features was actually still observed in the skewness and kurtosis. So just as an understanding, these critical few features are basically what the random forest classifier model finds to be the most useful in terms of creating a prediction for heart sound location. And the critical few features show that the first few filter bank energies and subband spectral centroids seem to be the most relevant as far as creating those predictions. As far as evaluating the model, we used a couple of different metrics. So across the entire test data set, we noticed that there was around a 90% accuracy. We can conclude this from the confusion matrix on the left. We also evaluated this model using precision and recall techniques, and we noticed that for each of the four valve classes, so there are four valves in the heart: the aortic, pulmonary, tricuspid, and mitral valves, represented as AV, PV, TV, and MV. We noticed around a 90% precision and recall as well for this stage one RFC model. So what this suggests is that the random forest classifier is successful at basically classifying what location of the heart a heart sound came from. Now this brings us into stage two, where we can basically create a prediction for the existence of a murmur in a specific valve of the heart. So remember, there are four valves in the heart, and for each of these valves, there's a separate random forest classifier model that's being used. And on this slide, you can basically see the ROC, receiver operating characteristic curves, for each of the four models. We do notice that across the test data set, there's around a 70% area under the curve for each of the ROC models, ROC charts. But across the full data set, we notice that each model is basically able to have an area under the curve of around 97-98%. What this basically suggests is that the random forest classifier model is successfully able to generally predict when a specific valve of the heart has a murmur. So in combination with stage one, this is able to produce a complete system for both murmur detection, heart sound location prediction, as well as murmur location detection. So Yes, so this basically is a successful implementation of the a random forest classifier model for predicting heart sound and murmur location. We do notice that the mitral valve dataset, with this is basically the second chart shown here from the left. The mitral valve ROC did have a slightly lower area under the curve compared to the other models. This is likely due to the fact that the entire data set, the CIRCOR Digiscope data set, has a slight bias against the mitral valve cases. There are simply just more aortic valve and pulmonary valve and tricuspid valve cases compared to the mitral valve. But in conclusion, this HM Detect software is basically able to give predictions in real time as far as basically the heart murmur location. And it provides doctors basically a feasible solution, especially in geographically, in areas where there's some geographic limitation from a doctor-physician access for diagnosing a patient given given a heart condition. And the random forest classifier is successful in this process. And in the future, we would basically like to extend this random forest classifier model and implement it in an application to test on real patients. We also would like to combine this random forest classifier model with digital stethoscopes so that even doctors who are using this digital stethoscope can basically have both like a computational prediction that can aid their own diagnosis of a patient. So with that, we would like to thank Dr. Yusridhar from India for providing some valuable insights on cardiovascular diseases, and thank you all for your attention.